All right, everybody, welcome back to the next video. Today's video will be on Hecke correspondences. This will be the first of a few different ways that we eventually view the Hecke operators, okay, as correspondences on curves. All right, so what's a correspondence? Well, the point is we have a basic understanding now of modular curves as isolated objects. So now we want to look at kind of correspondences between or on them. And a correspondence on a smooth projective curve X, it's just a triple, which we'll call T, given by Z, a smooth projective curve, and phi and psi, which are distinct non-constant morphisms from Z to X. So the picture I have in my head is something like this. Okay, so you've got your phi and your psi, both going from Z to X, and they're distinct non-constant morphisms. If K is a field, we'll say T is defined over K. If X, Z, phi, and psi are all defined over K, of course. All right. Here's a quick, stupid example. If I give you a delta in the automorphism group of X, this gives a correspondence on X. Just set Z equal to X, phi equal to the identity map on X, and psi equal to delta. All right, so you've got a map X to X given by the identity. You've got another map X to X given by delta. Okay, so here's our specific setup. Let's let n be a natural number. Let's let p be a prime. Let's let m be n and p. Let's let E over Q adjoint J be an elliptic curve with J invariant J, like the universal elliptic curve E sub J or something like that. And as usual, we'll fix a Z mod MZ basis for E bracket M, the M torsion of E. And again, as usual, this gives us an identification of the Galois group of the torsion extension of the elliptic curve E over Q adjoint J with GL2 of Z mod MZ, excuse me. Okay. Now, let's look inside this GL2 of Z mod MZ here. Let's consider the subgroup, which we'll call H sub P, given by matrices A, B, C, D in that GL2 of Z mod MZ, such that B is 0 mod N and C is 0 mod P. And remember, M is the least common multiple of N and P. You can check, you can see immediately that the negative of the identity matrix is in this subgroup. You can also check that the determinant map from HP to Z mod MZ cross is surjective. And so by theorem 2 from a previous video, the fixed field of H sub P has to be the function field of a smooth projective Q curve. We're going to denote that by X sub 0 of N comma P. Because remember, these function fields that we get this way using theorem 2, those are called modular curves. And so we'll notate this one that we get as such, X sub 0 of N P. So the Hecke correspondence T sub P on the modular curve X sub 0 of N, it's a correspondence over Q, which takes the following form. We'll call it T sub P again, and the triple is given by X sub 0 of N comma P, phi sub P comma psi sub P, where all I now have to do now is define these two morphisms, phi sub P and psi sub P. So here you go, I've got this picture here, X sub 0 N P to X sub 0 N, and I'll have two morphisms yet to be defined, phi sub P and psi sub P, and everything will be defined over Q, both curves and both morphisms. Okay, so T sub P, here we go. I gotta give you the morphisms now. The first one's easy. So let's let K sub P be the fixed field of H sub P, right? And let's let K be the fixed field of this other subgroup of GL2 of Z mod MZ, a little bit simpler subgroup. It's the set of all matrices A, B, C, D, where B is just 0 mod N. So H contains H sub P, because H sub P had additional restrictions on it. C had to be 0 mod P, but B still had to be 0 mod N in the definition of HP. So HP is contained in H. But that means, by Galois theory, K is contained in KP, right? The fixed field of H has to be contained in the fixed field of HP. Well, that's just saying K is contained in KP as an inclusion of function fields. Now, you know that an inclusion of function fields corresponds to a morphism of curves by the curves fields correspondence. This gives us a map, which we'll call phi sub P, from X sub 0 NP, which is just the modular curve X of HP, to XH, which is X sub 0 of N. You know this is X sub 0 of N because H here is essentially a carbon copy of gamma sub 0 of N. Okay, so here's a map from X sub 0 NP to X sub 0 of N. That's one of the two maps found in the Hecke correspondence T sub P. Okay, so there's our first map. We need another map to go from this curve to actually have a correspondence. So how do we do that? For the other morphism, we will consider a certain inclusion of function fields, K prime we'll call it, into KP, where K prime is a subfield of KP, which is isomorphic to but different from K. So we already have K going in here, giving us our first map. I want another field K prime going in here, okay, that's isomorphic to K but different from K. And that should give me a map from x sub 0 np to x sub 0 of n in the same way that k did. Okay, here's what we'll do. You need to recall that the Galois group that we're looking at, the Galois group Q adjoin J and the M torsion of E, where E is our elliptic curve of J invariant J, over Q adjoin J. That Galois group we know is isomorphic to GL2 of Z mod MZ, but this isomorphism is non-canonical. It depends on a choice of basis for M torsion of E over Z mod MZ. In other words, it depends on a decomposition of the M torsion of E into cyclic subgroups of order M, which we'll call C1 and C2. Okay, so that's kind of the setup. Now, let's let C denote the cyclic subgroup of C2 here, okay, of order N. I can do that because these are of order M, where M is the LCM of N and P, right? So that C2 definitely contains a unique cyclic subgroup of order N. And let's let pi denote the cyclic subgroup of C1 of order P, which exists and is unique for the same reason. Okay, you can easily check, and I won't do this, that C and pi are stable under the action of HP. And so by Galois theory, that just means they're defined over the field KP. Since pi in particular is defined over KP though, there's got to be an elliptic curve, which we'll call E prime over that field KP, equipped with a KP isogeny, lambda from E to E prime, with kernel pi. So this is covered in Silverman 1, chapter 3, okay? And then E prime, this new elliptic curve, that's the image under this isogeny lambda, this clearly has a cyclic subgroup of order and also defined over KP. I mean, you guessed it, it's just lambda of C, right? I mean, you had such a subgroup here, just take the image in E prime. It's defined over KP because everything else is defined over KP, all right? So, let's let J prime be the J invariant of E prime, which is in KP because everything up here was defined, over KP. And now let's take an elliptic curve E double prime, this time over a Q adjoin J prime that has J invariant J prime. So you can think of E double prime maybe as like a universal elliptic curve in this new notation J prime instead of using J. So there is then going to be a KP bar isomorphism, theta from E prime to E double prime, which is unique up to sign. This is basically because J prime is being viewed as a transcendental, so it's not 0 or 1728. Okay, so you can, if you want more details, you can see Silverman 1, chapter 12. Now, I've got lambda of C here. This is a cyclic subgroup of order N. If I look at C prime, which is theta of lambda of C, so it's the image of lambda of C under this map theta, so this lives in E double prime. Okay, this is a cyclic subgroup of E double prime of order N. You can check it's independent of choice of theta, basically because there's only two choices for theta anyway, and they only change up to sign. It's defined over KP since lambda of C is defined over KP, and since sigma compose theta compose sigma inverse has got to be plus or minus theta for all sigma in the absolute Galois group of KP. So this shows that theta is actually defined over KP like I'm claiming. And the reason this is true here is because, again, there's only one KP bar isomorphism from E prime to E double prime up to sign. Well, here's another KP bar isomorphism for each sigma. Okay, so all of these must be plus or minus sigma. Okay, so everything's defined over KP basically. Okay, and so that means, well, you can check. This is a quick little exercise, but it's kind of easy to see naively. KP actually contains the field K prime fixed by all of the sigma in the absolute Galois group of Q adjoin J prime that fix C prime. Okay, so I'll leave it as an exercise for you to translate all of the stuff I said above into this simple statement. Okay. Now, okay, so you can also see that K prime is isomorphic to the function field of x sub 0 of n. You see, because what's going on here is you're fixing a generic n torsion structure on the universal elliptic curve with J invariant J prime. That's what's going on here. Okay, well, the field fixed by that is the function field of x sub 0 of n, essentially by definition of x sub 0 of n. Okay, and you can also see pretty easily that K prime is distinct from but isomorphic to K. I mean, K, obviously it's isomorphic to K because K was also isomorphic to the function field of x sub 0 of n. And then it's not hard to see these are distinct either. Okay, and so this gives us another morphism psi sub p from x sub 0 of np to x sub 0 of n as desired. And it gives us this morphism in the same way that we got our first morphism, basically from the curves fields correspondence. We have an inclusion of function fields corresponding to a map of modular curves. Okay, the last thing I want to say for today is what happens for x sub 1 of n. you can see CSS page 63 for this. You can build a Hecke correspondence, which we'll also call T sub P, given by the triple x sub 1 of np, phi sub p, psi sub p, on x sub 1 of n, where x sub 1 of np is the modular curve whose function field is now the fixed field of the subgroup, which we'll call h prime sub p, which is given by all matrices A, B, C, D, and GL2 of Z mod MZ. This time, though, I don't just want B equals 0 mod n and C equals 0 mod p. I also want D equals plus or minus 1 mod n. Okay. And phi sub p and psi sub p, these maps from x sub 1 of np to x sub 1 of n, they're morphisms produced in nearly an identical way to the way we produce the ones for x sub 0 of n. You just use points of order n instead of cyclic subgroups of order n, as you would expect, because we're working with x sub 1 of n here. Okay, so next video, we'll look at all this moduli theoretically. So thanks for watching, and I'll see you then.